A very good morning to one and all. The topic on which I'm going to discuss is CSIR organic spectroscopic problems. Now, before going to the topic, I'd like to quote the words of Alfred North Whitehead. According to him, the aim of science is to seek the simplest explanation of complex facts. The facts may, however, be very complex, but it is ultimate aim of science to give a very simple explanation that's possible. So with that aim, let's move on to the topic. Now here, I'll not be talking about all the intricate details of the spectroscopic techniques. Here, I'll be just telling you or giving you an outline picture of the data that is going to be involved in solving the problems, assuming that you have already studied. Now, electronic spectroscopy is otherwise called as UV visible spectroscopy. Now, here, basically, it depends whenever an electron jumps from ground state to the excited state, it absorbs some energy. Now, depending upon where the electron resides, the transitions can take place. Especially in organic compounds, the electron resides either in the sigma, pi, or non-bonding orbitals. So depending upon them, you may have sigma to sigma star, pi to pi star, n to sigma star, and n to pi star transitions possible. But we are just bothered about n to pi star and pi to pi star transitions because they fall in the UV visible region. Next, Woodward and Fishers were the two scientists. What they did was they collected the data of all the experimental values and arrived at the theoretical calculation of the lambda max values. So they could calculate the lambda max values for conjugated dienes and alpha beta unsaturated carbonyl compounds. Now here you can see the base values of cyclic or heteroannular dienes, homoannular dienes, ketones, aldehyde esters, and the additive properties like the alkyls or alkyl residues, ring residues, we call it as. Each one will carry 5. And if you have an extra conjugation, you can add 30. And if you have exocyclic double bond, depending whether it's on the 1 ring or the 2 ring, you can add either 5 or 10. Now coming to the IR spectral data, IR spectroscopy is otherwise called as vibrational spectroscopy. Now here, it depends, like mostly we are worried about the regions ranges from 400 to 4000 centimeter inverse. And here we are just bothered about 1500 to 4000 centimeter inverse because that region is known as functional group region. So for solving the problems, if we know those values, that's enough. Mostly we are bothered about OH frequencies, NH frequencies, and CH, carbon-carbon single bond, double bond, and so on. Next, a very important technique for organic molecules is NMR spectroscopy, both proton and C13 NMR spectroscopy. Now, when you talk about proton NMR spectroscopy, here in the region when you say like from right to left, your values increases from 0 to 12 or 13 del value. So mostly you'll have in the upfield alkyls followed by allyls, and then you have alkynes followed by vinyl. And in between, depending whether it is attached to an electron withdrawing group, it will be slightly deshielded. When it is attached to an electron negative element, it will be highly deshielded. Now, when you talk about carbon 13 NMR, here this is from 0 to it ranges till 250. And here again, you have alkanes, alkenes, and alkynes followed by aromatic. And this is carbonyl group. So here you have the values for all these things. Okay, that will tell you how many different kinds of protons or different kinds of carbon atoms are present. But if you want to know the characteristic of the neighboring group, then you have to look into the spin splitting. Now the signal splitting, if you see here, the formula is 2Ni plus 1. And here I stands for I is equal to half. So for proton, it is I is equal to half. So depending upon the number of protons, you may have a singlet, doublet, triplet, quartet. and these are the intensity ratios. Now, when you have coupling due to the spin I is equal to 1 value, then you have this kind of splitting patterns, and this is the intensity ratio. Fine, when they split, then what is the coupling constant? That is the distance between the two split up peaks. Now here, when you have free rotation, it is 6 to 8 hertz. When you talk about alkenes, the geminal hydrogens will have a very low coupling constant, 0 to 3. When you talk about cis, it is 6 to 12, and trans is 12 to 18. And when you talk about aromatic group, you have three possible positions, either orthocoupling, metacoupling, or paracoupling. Orthocoupling is quite significant, 6 to 10. Meta is 0 to 1 to 3, and para is highly insignificant value. Now, besides this, you can also know about the Karplus equation. Now, from Karplus equation, basically you can calculate what can be the J value. Now, here we have written it as 3. That means the dihedral angle, the coupling constant depends on the dihedral angle, and what do you call as dihedral angle? The angle between the alternate bonds, first and the third bond. Now, here if you see, when the dihedral angle starts from 0, it can have J value from almost 8 to 11, and it decreases, and when you arrive at 90 degree, it's almost 0 to 1.5 or so, and it starts increasing when you reach the dihedral angle of 180 degree. It ranges from almost 9 to 13. So this is the values which you remember. And for cyclohexanones, generally cyclohexanones, when you have an axial equatorial, the dihedral angle is 60, equatorial it is 60, and when it is diaxial, it is 180 degree. The ultimate technique for organic compounds is mass spectral data. Now here, if you look, the molecular ion peak will tell you or give you an information regarding the molecular weight, molecular formula. And the most intense peak will be the base peak, that is due to the stable carbonium ion that's being formed. And when you have M-18 means loss of proton and loss of hydrogen. And whenever your compound is aromatic, if a phenyl group is there, you will get a peak around 77, and this is tropylium 91, and anilinium, it is C6H5NH2 plus, you have it as 93. Fine. So this is the simple data which is required to solve the problems. Besides this, an important thing which you have to keep in mind is isotopic peaks. See, mostly you have M or M plus 2 peaks because of the isotopes, and we are just concerned about bromine, chlorine, because they have the relative ratios are quite significant. Because for bromine 79 and 81, it is 1:1 almost ratio. If you consider this is 100, this is 97.9. For chlorine, it is 132.6, so it is 3:1. When you have bromine, 2 bromine are there in your organic molecule, then you'll have 1:2:1. When you have 2 chlorines, you'll have 9:6:1. So that kind of a thing, you can basically calculate it. That's it. And as I said, the base peak can be due to the stable carbonium ion or due to the McLafferty rearrangement that takes place due to the abstraction of the gamma hydrogen, and you get a peak. Now, how to solve spectroscopic problems? Now, suppose if the molecular formula is given, you can basically find out the degree of unsaturation or double bond equivalence. Now, when you consider here CXHYNZO, where X is the number of tetravalent species, Y is the number of monovalent species, and Z is the number of trivalent species. So you can calculate the double bond equivalence by using the formula X minus Y by 2 plus Z by 2 plus 1. Now, when you consider for this particular formula, here your X is 5, your Y is 5, and Z is 1. When you substitute here, you get a value of 4. That means either you can have 4 double bonds or 2 triple bonds or a ring with a 3 double bond. And here this molecule is nothing but pyridine. When you look here, you have a ring and 3 double bonds are there. Second is you look at the IR to find out whether what functional groups you have. The major functional groups you can check and then disconfirm or confirm by using NMR. When you come to the NMR, first thing is you look at the peak around 7 because that shows the presence of an aromatic moiety. And then you go for the multiplicities and coupling constants. So based on that, you can ascertain the nature of the neighboring group. So by doing so, you can discard certain options and then you see if mass spectrum is given, you can check it and discard the other options. Once you think that you have the one that may match, you can go back and check it because each mark is very important. When you take a problem of 4 marks, if you answer it correctly, you are going to fetch 4 marks. If you're going to answer it wrongly, you're going to lose 1 mark. That means you're not only losing those 4 marks, but you're going to lose 1 mark from whatever you have gained earlier. So it's better to go back and recheck once you know what it is. Now to start with, I'm going to just discuss about few problems and then we'll go to the CSIR problems. Now in this, in the UV visible spectrum, a diterpenoid exhibits a lambda max at 275 nanometer. The compound among the choices given below here are, you have been given 4 options. Now when you consider the first option, here it is heterocyclic double bond. And we know the base peak, it is 215. But here it is 275. So this may not be possible. Next, when you come to the option B, here you have 2 double bonds, but they are not conjugated. There is a break in the conjugation. So here again, it is not possible. When you come to option 3, here if you see they are homoannular dienes, you have both the double bonds in the same ring. So it may have, but we have to work it out. Now you go to option D. Here the double bonds are not in a homoannular. So again here the base peak is 215. So this may not work out and result in 275 nanometer. So we'll just consider C. Now here the base value, as you have seen here, is 253 because it's a homoannular. Now when you want to consider the ring residue, you have to see how many ring residues you have. Now this is a homoannular diene, so this is 1, 2, 3, 4. So totally you have 4 ring residues. So 4 into 520. And how many exocyclic double bonds when you consider the hexocyclic double bond? This is an endocyclic double bond. It belongs to this ring. This double bond of course belongs to this ring, but it is outside this ring. So this is a hexocyclic double bond. Since it is 1 hexocyclic double bond, you're going to add 5. So that works out to be 278 nanometer, which is very close with the observed one. So your answer will be option C. Fine. Now let's go to the second problem. In the molecules given below, the relationship between the chemical shifts of HA and HB will be. So when you look at the options, either they are equal or they are one is greater, the other one is greater. But when you look at the molecule as such, superficially you feel they are same, then we may be tempted to answer it as same. That means option A. But when you just look at it very closely, here you can see HA is just above this pi electron cloud, whereas HB is in the plane of the pi bond. And we know when you have, it lies in the cone of the pi electron density, then it will be shielded. So your HA will be shielded, whereas since this lies along the plane, so this one will be de-shielded. So de-shielded means the value will be higher. So we know the HB value will be greater than HA. In that case, your answer will be option B. So not in all the cases you can discard options. In certain cases, you have to work it out and arrive at the answers. Now here, when the cyclohexane given below is dissolved in benzene, hydroxy group forms hydrogen bond, intramolecular hydrogen bond with the carbonyl. But the same when dissolved in methanol, it does not form intramolecular hydrogen bond. The coupling constant JAB in methanol will be. So they have given you certain conditions that in one solvent it forms hydrogen bonding, the other one it doesn't. So here you have to write the different conformations that are possible. So since in benzene hydrogen bonding is possible, so this can be the geometry that will be adopted by this. Now here if you see OH is forming intramolecular hydrogen bonding and HA is in the equatorial position and HB is in the equatorial position. Now here it does not form hydrogen bonding in methanol. And if you look at the positions of HA and HB, they are in the diaxial position. Fine. We know according to the calculus profile that if the dihedral angle is 180 degree, then your J value will be around this region, 9 to 13 hertz. But if they are in the equatorial, that is the dihedral angle will be 60, and here you will have it as this hertz. So finally, what you can see is, since the question is asked for methanol, and in methanol, the calculus, according to the calculus equation, you have it as 9 to 13 hertz. So your answer will be 11 hertz. So that is your correct option. Now, in the compound given below, the relationship between the chemical shift of HA and HB are. Now, when you look at the molecule, don't bother about its name or whatever it is. Simply see. Now, here again, when I see hen, this is CH2. So, for me, both of them, they look alike. So, you may be tempted to call it as HA is equal to HB. But again, here, if you see, HB is in a very cool environment, whereas your HA is in a highly strained condition. The reason here it is, this HA is very near to the bridge head nitrogen. And whenever you have the hydrogen in a strained region, then that will be de-shielded. So de-shielded means that will have a higher delta value. So compared to HB, HA will be de-shielded, so HA value will be greater than HB. And if you see, HA is around 5.45 and HB is around 2.91. So what will be your answer? HA is greater than HB. So your correct option is option C. Next, we'll move to the fifth problem, which is from June 2019 CSIR question. Now here the compound that exhibits the following spectral data is. So they have given you IR, proton NMR, C13 NMR and mass spectrum. So with that, we'll go on to solve this. Now to start with, your IR value 1685, so it has to be a carbonyl group. And when you look at all the options, you do have carbonyl. And next, when you look at the proton NMR, here when you have around 7 range, then you can say aromatic groups is present. And here, this is for 2 hydrogen, and at 7.6 you have for 2 hydrogen. And if you see the splitting, it's doublet, it's also doublet. And what is the coupling constant? 8 hertz. So when the coupling constant is 8 hertz, in that case, you can be sure that it is undergoing orthocoupling. So you have 2 sets of protons and both are having orthocoupling. So it goes without saying they have to be di-substituted, and the position, relative positions will be in the para position. So when you look at the options, straight away, I can discard option B. So we are left with A, B, and C. Next, when you look at this 3.62, it is for 2 hydrogen and it is triplet. So when you say 3.65, that means it's highly d-shielded. It has to be next to an electronegative element, and it has another neighboring group which has got CH2. That is why it is split into triplet. Now when you look here, here you have find one CH2. Here also you have one CH2. But this CH2 is next to your carbonyl group. This is electron withdrawing group and not electronegative element. So you can rule out option C. Now you are left with option A and B. If you look at the mass spectrum, here you have something 1:1. So the bulk fragment contains bromine. Since we know the relative abundance of bromine 79 and 81 is 1:1, so that will be possible only when you have bromine attached to the phenyl. So this molecule, since it is alpha, carbonyl group alpha, beta, gamma, it can undergo McLafferty rearrangement to give you a stable carbonium ion. And in that way, the bulky group has to contain bromine. So you can omit option B and your answer will be. So it's very easy. But anyway, as I said, you go back and recheck it. And when you look at the values, this is highly d-shielded and this is slightly d-shielded because it is next to your electron withdrawing group, and this is aromatic moiety. And this is, I have just indexed all the C13 NMR. You can just go through it afterwards. And okay, for your understanding, if you want, I can just say here it is 45. The CH2 is de-shielded compared to this 28. It is slightly de-shielded. And carbonyls, generally it is from 190 and above. And this is aromatic region. And because of this McLafferty rearrangement, you have 198:200. That is 1:1. And you have another one, bulky group, 1:1. So with that, we'll move on to the problem number 6. And this is a question from December 2018. Now here the structure of the compound displaying following characteristic spectral data, they have given you the IR and proton NMR values. So 4 options are here. When you look at 1720, this 1720 is very much characteristic of alpha beta unsaturated carbonyls. So in that way, when you look at the options, you can see A, you don't have alpha beta. So you can rule out option A. B, you have it. C, no. So you can rule out. So you're left with option B and D. Now 1.1 triplet 3 hydrogen, that means 3 hydrogen. So it has to be a methyl group, and since it's a triplet, it has to be next to a next neighboring group has to be CH2. Fine. Next you have 3 hydrogen singlets. So this indicates that again you have a methyl group which is next to your alkene group. Fine. So you call it as allylic also. So in this way you can rule out option B. And you're left with option B, which you think it can be correct, and you just work it out. If you see, this is methyl group, terminal methyl group. It is a methylene group attached to electronegative element. And here you have the double bond. Here this methyl group attached to this allylic one, you have it as 2. And between these two, they are same, attached to the same carbon atom, but you can see the shift. It is 5.5, whereas this is 6.2 because it lies just above this your pi cloud. So that is why it is D-shielded. So your answer is B option. Next, question number 7. Partial spectroscopic data is given below for an organic compound. Now here they haven't given you each and every values. They have given just you have 4 signals in this region. That means you have 4 signals in the aromatic region and 2 doublets in this region. When the word you see 2 doublets in the aromatic region in the proton NMR, you can be sure that it has to be para-substituted. Now you look at the options and see, when you see this is not para-substituted, you can omit it. B para-substituted, C is not para-substituted, so rule it out. D is of course para-substituted. So your option is going to be between B and D. Now when you look at the IR value, it is 1724. That means it suggests that it has to be alpha beta unsaturated carbonyl. Now here between B, you have alpha beta unsaturated. Here you don't have it. So you can just rule out option B and your answer is option B. Just check it. Totally, how many signals are possible in C13? 1. Okay, we'll just bother about proton NMR. Proton NMR 1, 2. C13 NMR 1, 2, 3, 4. So in the aromatic region, you have 4. Fine. Let's move on to the next question. In the IR spectra, the stretching frequency in centimeter inverse of the carbonyl group of the following compound is in the order. Now you have been given 3 options A, B, and C. Now among these 3, you have to arrange them in the decreasing order of their stretching frequencies. Now when you look here, here you have resonance possible because of the conjugation. Here you don't have resonance possible, and here of course you have resonance possible due to conjugation. So we know resonance lowers the frequency. So obviously C and A will have lesser frequency compared to your B. So when you look at the options, I can omit B and D. So you're left with option A and C. Now the problem is B is first you have found out. Now between A and C, which one will be which one you're going to see will have lesser or the higher. Now here also you have a conjugation, here also you have a conjugation, but here you have a trans conjugation, here you have cis conjugation. And we know trans conjugation is much more easier and favorable one. So this conjugation takes place in a very facile way. So this molecule will have a lesser stretching frequency than C. So A will have less. In that case, you're going to discard option A and your option is C. Now this is for your understanding. I have just given the values, but anyway, you cannot just mug up all the values. Okay, fine. Here I just want to give you an explanation for that earlier question. See, when you have an minus I inductive effect, that means it just tries to drain out the electron from the carbonyl group. When it drains out, here the bond order increases. So the stretching frequency will increase and you will see an increase in the stretching frequency of carbonyl. But when you have resonance possible, so this comes over here and this goes, and here the bond order decreases. So the stretching frequency decreases and you see a decrease in the stretching value. See here when the lone pair of electron comes in due to resonance, also due to the I effect. So here it is draining the electron, it is giving the electron. That's it. Next, we'll see June 2018 question paper. In this, we have a question. A compound shows following spectral data. Now here you have proton NMR alone and mass spectrum is given. And you have been provided with 4 options. Now when you look at the NMR, first thing what we see is in the aromatic region. If you see here, it is for 2 hydrogen, which is a doublet. Here again 2 hydrogen, which is a doublet. So it goes without saying they have to be para-substituted. Now you look into your options and see whether all are para-substituted. You can see that C option is not para-substituted. So you can rule out C, also B. Fine. Now between A and B, which one? So you can start assigning the values also. But here if I see, there is something 92 a peak is there. And we know carbonyls generally they undergo alpha cleavage. And if it undergoes alpha cleavage, this can be possible. C6H4NH2, that is 92. So you can discard option B and your option A can be correct. So this is the mass alpha cleavage. This has been given and this is due to the McLaughlin. So that rules out your option A, sorry, B, and the correct option is A. Here, this point I wanted to highlight. See, whenever you have a broad one, it just signifies that it can be NH2 because the I value of N is 1. And moreover, if you would have seen in the question, it was given exchangeable, D2O exchangeable. So whenever you have OH or NH2, it just exchanges with your hydrogen and you don't get a peak for that. And even if you get a peak for it, they wouldn't have done it in D2O. If they would have done it in D2O, you wouldn't have observed this peak. That's Next, we have a question from December 2017. The organic compound that displays the following data in proton NMR. So just you have to see about proton NMR. Now here you have two doublets again in the same region. I don't know why. Almost all the CSIR questions you have para-substituted compounds. So for whatever we have seen. So when you look into the option of, I can rule out option D because it's not para-substituted. Next, when you look into 1.29 singlet, so besides this, you have only one signal. So when I look into option C, I have one over here, besides aromatic, the other one possible here, and these two same. So three more signals I'll expect. When I come, so I can rule out this. Okay, come to B option, here I'll expect one signal, and I'll expect these two same signals. So I'll be expecting two signals, but here you have only one. So I can just rule out this. And when you come here, I'll expect, okay, all these three will have only one. So that is 1.29 singlet because you don't have a neighboring hydrogen here. So your correct option is A. So this is what we have assigned here. Next is a question from June 2017. Here, the correct structure of the compound based on the following characteristic spectral data. They have given IR, proton NMR, and C13 NMR. Fine. So when you see 1736 centimeter inverse, it has to be alpha beta unsaturated carbonyl. Okay. So that means ester, slightly higher than. So I can omit B, A, but let's wait and see with the others. Now here you have 3.56, which is a singlet and accounts for 3 hydrogen. So it has to be a methyl group, which is attached to an electronegative element with no neighboring hydrogens. So here you don't have a methyl group. Here you have a methyl group. Okay. Here you have a methyl group. Here you have two methyl groups. So I can just omit option A, option B, because here two methyl groups are there. And again, like if I look this as electron withdrawing, I could have omitted this also here because it should be around 2 point something, but let's see. Next, you have 3.32 triplet for 2 hydrogens. So when you have 2 hydrogen, they must be attached to an electronegative element and neighboring group has to be CH. You have another 2.25, which is a triplet, and it is attached to CH2. It has to be attached to an electron withdrawing. So here, your CH2 and this CH2 both are attached directly to an electronegative element. Whereas here, the CH2 is attached to an electron withdrawing group and this CH2 is attached to an electronegative element. So I can discard option B and your answer will be option C. Just see, these are the values which we have assigned for proton NMR and C13 NMR. Next is question number 12. Carbon 13 NMR spectrum of DMSO-D6 gives a signal at 39.7 ppm as a. So they have given you, it is going to give you only one signal and the delta value is also given, only you have to find out the splitting. Now first you write the structure. Now if you see, you have 2 carbons and when you look at them, both of them are identical. So that is why they have given you only one signal. And here we know for C13 NMR, it is the group which is attached to it, either hydrogen or deuterium, which undergoes the splitting. And here you have deuterium. So when you have deuterium, you know I value for deuterium is 1. So you just substitute the value of I into Ni plus 1, where N is how many deuterium you have? 3. And I is 1. So just substitute 2 into 3 into 1 plus 7. That works out to be 7. So your option B is correct. Now let's move on to a question from December 2018. Now here, one second. Now here, the compound that exhibits following spectral data is proton NMR. Data is given to you. Fine. Now when you look at this, again will be J value. You see the aromatic compounds region. 7.7, 6.8. You have for 2 hydrogen a doublet, for 2 hydrogen another doublet with a coupling constant of 8 hertz. So it shows that ortho coupling is there. So it has to be para substituted. And when you look at the options, straight away you can rule out option 1 and option 2. So you are left with option 3 and option 4. Now here, fine, you have this one de-shielded and this is slightly de-shielded. Now here, besides that, you have, okay, 8 1 proton is there, trans, that is 12.3 and here 12.3. Okay. And if you see here, there is one methyl group which is attached to an electronegative element. So both are present in here and here. And here, all the 6 hydrogens are same. Now here it looks like, okay, fine, these two are identical. And here also these two look identical. But here one factor you have to think is, see here it has got a lone pair of electron. So this lone pair of electron can shift here. So it will form a C double bond C and this bond will shift here. Okay. So with respect to the O minus, one of the methyl will be trans, the other methyl will be cis. So these two will be non-equivalent set of protons, but here the data is given as equivalent, they are same. So you can just rule out option 4 and your answer 3 has to be the correct option. Fine. So here you can see now these two are identical and when you go here, you have these two and here again this is de-shielded because it lies in the pi electron cloud region. So that is why it is de-shielded. Fine. Question number 14. Now the proton NMR spectrum of a mixture of benzene acid and acetonitrile shows 2 singlets of equal integration. The molar ratio of benzene is to acetonitrile is. Now you consider benzene. So when you talk about benzene, the formula is C6H6 and for acetonitrile CH3Cl. Now since you're talking about proton NMR, how many protons you have which are identical? 6 and here 3 protons. So I will expect the integration ratio to be 2:1. But actually what they're saying is they have to be 1:1, equal integration. So 1:1 means if this is for 6 proton, this also should be for 6 proton. So how it is possible? When you take twice the amount of this. So when you take twice the amount, then you'll have 6. So it is 1 equivalent and this is 2 equivalent. So your correct answer is going to be option C. Fine. Let's move on to question from June 2016. Here the question reads as follows. In the UV visible spectrum of an alpha beta unsaturated carbonyl compound with increasing solvent polarity. Now here you have been provided with 4 options. And when you look at the 4 options, definitely N2 pi star and pi 2 pi star are not going to behave same. So I can just rule out at first rule out 3 and 4. So between 1 and 2, if you have been thorough enough, you can directly click option 1. But anyway, I'll just, for the sake of class, I'll take it and then we'll go to the answer. Now, when you see your molecule is a non-polar solvent, this is the energy level of non-bonding orbital, and this is the energy level of pi star. The moment you dissolve it in a polar solvent, your non-bonding electrons are being involved in the hydrogen bonding with the polar solvent, and they are highly stabilized, and the energy is decreased too much. And this is slightly decreased because it's also polar. So as a result, the energy difference between C and D and A and B, if you compare, the energy of CED is greater than AB. And you know E is equal to H nu or E is equal to Hc by lambda. If energy is greater, then wavelength has to be lesser. So you expect a blue or hypsochromic shift. So when you look at the option hypsochromic shift, so which one is your correct answer? Option A is correct. Option 2 is wrong. Anyway, but when it comes to pi star, here if you see between pi and pi star orbital is more polar. So that will be slightly stabilized more compared to your pi orbital. So as a result, the energy level between n and pi to pi star in polar solvent will be less, or you can say when energy is less, the wavelength will be high, so it will exhibit red shift or bathochromic shift. Now we'll move on to question number 16. Here, a compound displays the following spectral data. The correct structure of the compound is, they have given you 4 options, and you're provided with IR value, proton NMR, and C30. Fine. Now here you just look at the values that's given. In proton NMR, when you see, yeah, 6.9 and 7.8. As usual, if you have been looking, you can see that all are para substituted. I don't know why the question paper setter has got a liking towards the para substituted compounds. I can rule out option 3, left with 1, 2, and 4. And next, when you look at the C13 NMR, now here C13 NMR, you have 197 and 165. It is always like when you have ketone carbonyl compounds, it is generally 197. The same carbonyl compound in ketone, it is 190, and for ester, it is 170. And here you don't have for ester, so at one go, I can rule out option 4, option 2. So I'm just left with option 1, which is ought to be correct. Anyway, I have to recheck it. When you see, this is a methyl group with 2.5 because it is attached to an electron withdrawing group. And you have 2 groups here, 7.8, and this is 6.9, which is attached to this O-methoxy group. And this is a proton NMR values. You can, C13 NMR values. So here it is 26, where it is attached to an electronegative element. So it is 36, and you have all this one. Fine. Next, we have a question from December 2015. Here, the structure of the compound that matches the proton NMR data given below is, you're being just provided with the proton NMR data. Now here, we'll start with one by one. Here again, okay, fine. Here you have doublet of doublets. So at one go, we can say it's not para-substituted or di-substituted. We will see. Anyway, in aromatic, you have 1, 2, 3. So it is clear that it is tri-substituted compound. All are. And when you look, all are tri-substituted compound. And this is broad, as we saw, 6.5 broad, singlet 2H. Next, 3.8, you have it for methyl, and since it's a singlet and highly de-shielded, it has to be attached to an oxygen or electronegative element. So when you look at all the options, you have OMe, 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 but that's not there in option D, so you can rule out option D. Now, when you see 7.75, that is a highly deshielded one. It is for one hydrogen, which is doublet of doublet, and it is coupled by ortho because 8.8 and 2.4 meta. Next, you have 7.8. Here it is doublet. Fine, it has one neighboring, only meta coupling since 2.4. And 6.70, it is 8.8, only ortho coupling. Now, when you look A, B, and C, here you'll expect 1, 2, 3, and the ortho coupling will be there, doublet of doublet. But here this is not highly deshielded. Okay, and here only ortho coupling is there, and here no meta coupling, so I can just rule out this. Now you are left with A and B. Now between A and B, which one is highly deshielded? This one and this one. The highly deshielded should have a ortho coupling and meta coupling. Now here you have only ortho coupling possible, not meta. But here when you have a deshielding one, you have ortho coupling and meta coupling. And this one will have only meta coupling, this one will have only ortho coupling. So you can just rule out option D and A, and your option A is correct. Now just look at the values. This is a highly deshielded one, which is being coupled by ortho hydrogen and meta hydrogen. And this is coupled by only meta hydrogen. This hydrogen is coupled by only ortho hydrogen, and these are the other values. Question number 18. In the mass spectrum of 1,2-dichloroethane, approximate ratio of peaks at M by Z values 98, 100, 1 or 2 will be. Now this is dichloromethane. We'll see you have two chlorines. Now two chlorines means the 98 is M peak, this is M plus 2, this is M plus 4. So one of the option is both the chlorine can be 35. The other option is one chlorine 35, the other chlorine is 37. It can be either way, like this. And the third option is both are 37, 37. Fine. Now, when you talk about the relative abundance of chlorine 35, it is 3, and for 37, it's 1. Now, here if you see 3 into 3, 9. Now, here it is 3 into 1 plus 1 into 3, that's 6. Here 1 into 1, so 1. So what is your option? 9 is to 6 is to 1. So your answer is B option. Fine. Otherwise also, if you have a slight hinting, it cannot be anyway. Let's not take this. That's right. Now June 2015 question. This is a organic compound shows following spectral data. You have been provided with IR values, proton NMR, C13 and mass 2. Now, it's not always like you start with IR value. You can also go with the mass value. Now here, when you look at the mass value, here the M and M plus 2 peaks are given. And here the ratios, if you just see, it is 100 is to 4.9. So that gives you a clear indication that sulfur has to be present. And when you look at all the options, option A does not have sulfur, so I can rule out. And option C does not have sulfur, so I can just rule out. Next, when you look at the C13 NMR, you have 190. When you have 190, that means a carbonyl group has to be there. Okay, but when you look at option B, you have C double bond S, which will be around 170 to 180. So we can just rule out this option, and your correct answer is D. Anyway, we'll just work it out and see. You can see here 2.50 triplet, it's a singlet, and these are the aromatic protons, all are for 1H, and C13 NMR, if you see 28, 190, and this is in the aromatic rate. So whatever you have assumed is the correct answer. Now we'll have one more question from December 2014. Here, an organic compound having molecular formula C10H12O2 exhibits the following spectral data. You have been provided with IR, proton NMR, and C13 NMR. Now also you have been given with 4 options. Now when you look at the NMR values in the aromatic region, when you see, you have for 1H, 1H, and 1H. That means they have to be tri-substituted, and all are tri-substituted. So fine. Next, when you look here, here you have something called as 18 hertz. Now 18 hertz means it is, as in the earlier slides you have seen, that it is due to transcoupling. So by looking at this, you can just omit out the second one because first, third and fourth will have transcoupling. Okay, so you have this option. Next, when you see, you have 3.8 3 hydrogen singlet. So it should have a OMe group. Now when you look here, here you have OMe, here you have OMe, here you don't have OMe. So I can rule out option. Now you are left with option 1 and 3. Now here if you see, you should have in the aromatic region 3 hydrogen. Now I'm just using the data by which I can discard certain options. Now here in carbonyl group, I'll have 1, 2, 3. And this one will be doublet of doublet. This one will be doublet, this one will be doublet. But here you can see you have one singlet. Here they are not taking care of metacoupling. Now when I come here, this one will have orthocoupling, fine. And this one will have orthocoupling, so it will be doublet. You have a doublet here and you have a doublet here. And when you come here, here you will have a singlet that is here. So you can rule out option 3 and your correct option is option 1 if you see the data that's given here. Okay. This is a C13 NMR. Now the last question is from June 2014. Here you have the correct C13 NMR chemical shift of values of carbons labeled A to E in the following ester R. When you look at this, first thing is you look for the carbonyl one. And you know for carbonyl, it has to be around 190 region. So you look at the options B. Highest one should be carbonyl ester. Since it is an ester, it has to be around 170. Okay, carbonyl and it's an ester. Carbonyl group shows a maximum value around 170 here. So I can just omit option A and B. So you're left with C and D. Now when you see here, C and D, they are alkynyl hydrogens. So the value should be from 120 to 150. And between C and D, D should be highly de-shielded because of this carbonyl group. So when you look at the value B and C, sorry, C and D. C and D, which is highly de-shielded, D. So you can omit C and your correct answer is fine. This is what you have assigned. So next we have one more problem. Anyway, just an organic compound gives spectral data, following spectral data with IR, proton NMR and C13 NMR. Now when you look at these compounds here, at one go you can see like when you have aromatic, so they have to be para substituted. And when you look at the compounds, all are para substituted. Fine. Next is you have, so when you look here, NH is not there in the IR data, but here you have NH, so you can rule out option B, isn't it? Because you have NH here. So you are left with A, B, and C. And maybe when you look at the C13 NMR, you have only one highly de-shielded carbon. Okay, so in that way, I can rule out option B. Now between A and C, if you see A and C, here you have a metal group. Fine, proton NMR presence of, okay. When you have presence of CH2 next to the electronegative element on one side and on another side, electronegative element, CH2 group. So now CH2 group here you have a quartet, but it is highly de-shielded. So it has to be next to an Ca oxygen. So in that way, you can just rule out option A, and your correct option seems to be C. And when you look at this, of course it is C, and you look at the values, this is highly de-shielded and this is slightly de-shielded. Okay. So with that, I thank you all for your patient hearing.